20 right now, participants.
Nice attendance from POSOCO, Senior Simmons, Rajiv ji.
Satish, were you able to follow up with Dr. Sen?
No, Manish sir told that he's following up, and they will be joining from different systems.
Can you make them a panelist, Manish?
Yeah, I don't think he's is Manish Kumar from GE. I don't see.
No.
Okay. Yeah. No, it's General Electric.
Okay, I thought General Manager.
Okay, we are live, huh? So we are 3:03. Should we start or wait for Dr. Sen?
Maybe a minute, then we can start, Manali. 3:03 we can start. It's already 3:03 now. I think let's start. I mean, we'll invite him when he joins in.
Okay, sounds good.
Yeah. Nivedita, we can start the recording, please.
I think Nivedita has already done that, started it. Okay, so good afternoon, everyone. Welcome to the Knowledge Dissemination Workshop, Analysis of Battery Energy Storage System Applications in Transmission System. It's a pleasure to welcome all of you to today's webinar. This workshop is being organized as a part of USAID's Greening the Grid RISE initiative, RISE, which basically stands for Renewable Integration and Sustainable Energy. GTG-RISE is a bilateral program between USAID and Government of India and was started sometime in 2016 with the intent to support GOI's effort on large-scale integration of renewable energy. As a part of this initiative, a number of pilots are being undertaken in partnership with Government of India and its various institutions. Today, we are assembled here to talk about one of the pilots, to discuss the results of one of the pilots, basically the battery energy storage system, which we had, for which we have partnered with Power Grid Corporation of India Limited. We are still awaiting, Dr. Subir Sen to join us, but I'm hopeful that he'll be very soon joining us. Another thing which I wanted to make an announcement is Mr. Mrityunjay, the Joint Secretary Transmission, who was supposed to deliver the keynote address, is also unwell and will not be able to join us. It's very tiring time for many of us who are going through difficult situations. So we really appreciate whoever has made the time to join us today. It really shows your commitment to be a part of this whole journey where India is making the transition towards more clean energy, and US government, specifically USAID, is really very fortunate to be a partner in this whole journey. So without further ado, let me just start the discussions. And before that, we just quickly make a note that the recording, the workshop will be recorded, and the recording has already started. Request all the speakers to keep themselves on mute. We have kept some time for the questions, so please do put your question in the Q&A box, which would help or facilitate our moderator Shubhranshu to pick up your questions. And we hope to, as our normal trend, we will make a recording of the webinar, a proceeding, and we'll be circulating it within a week of this event. This is the first in the series of our BESS pilot, sharing of results of BESS pilot. So today we will share the results which came out of the actual various use cases applications which was done under grid condition and day after we will be sharing the results of a modeling study which we did for battery energy storage system in the southern region. So please tune in also for that. That would be we will really be grateful. So with that, let me just welcome Ms. Julia Kennedy, who is the Indo-Pacific Office Director at USAID India. Julia Kennedy has been now in India for nearly 4 years, and before this, she has also served in USAID in Haiti as well as Ecuador. And Julia also has the experience of working with the Department of State in the climate change negotiation team, and was also a Peace Corps volunteer. I'm really delighted to welcome you, Julia, for delivering the welcome remarks. So over to you, Julia.
Thank you, Manali. I'm delighted to be welcomed by you, so I appreciate it. So I want to wish everyone a very good afternoon. On behalf of the United States Agency for International Development, or USAID, I'm very happy to welcome you to the Knowledge Dissemination Workshop on the Battery Energy Storage System, or BESS application in transmission systems. Given the challenging COVID situation we are all experiencing in India, I really want to start by wishing everyone well and thanking all the people who continue to persevere and make progress in this important work, despite the challenging conditions. It is great to celebrate progress where we can, and this pilot, the successful completion of this pilot, is a great example of that. I'd also like to extend a very warm welcome to the distinguished representatives who are present today, including Mr. Baba, the Chairman and Managing Director of the Power System Operation Corporation, or POSOCO, and then when he is able to join us, Dr. Shubir Sen, the Chief Operating Officer for the Central Transmission Utility and Smart Grid Power Grid Corporation of India Limited, or PGCIL, and then of course, a warm welcome to all of you. Today's knowledge dissemination session comes after the successful go-live demonstration of the pilot at PGCIL's BESS facility in Puducherry in December 2020. I was privileged to be part of the go-live event with many of the esteemed guests who are present today, and so I'm very excited to hear about the learnings from the various test runs conducted over the last few months. Recently, the U.S. Special Presidential Envoy for Climate, John Kerry, visited India and met with all the key stakeholders, including the Minister of Power and Renewable Energy, Mr. R.K. Singh. At all the meetings and events, he really praised India's leadership in the clean energy transition and its efforts to meet its nationally determined contributions under the Paris Agreement. Special Presidential Envoy Kerry and Prime Minister Modi reaffirmed our two nations' shared desire to combat climate change, and as well as our complementary strengths. Together, the United States and India can creatively collaborate on a 2030 agenda for clean and green technologies in service of the planet. The visit underscored the value of enhanced bilateral cooperation across multiple areas, including mobilizing finance to support clean energy deployment at scale, and collaborating on innovation and scaling up emerging technologies, particularly things like energy storage. So that leads us back to today. Globally, the significance of clean energy storage technologies is fast gaining momentum with the increase in renewable energy generation. A recent International Energy Agency special report on India noted that India is likely to become the global market leader in solar and storage by 2040. Considering this, the BESS pilot undertaking as part of GTG-RISE assumes national significance. Implemented in partnership with PGCIL, the pilot demonstrates an array of BESS applications to validate its various usages in the Indian grid. This pilot is an attempt to build the evidence base for policy and regulatory frameworks, strengthen capacities, and incentivize private sector engagement that may support deployment of energy storage in the power system in the near future. In our view, this will strengthen energy security and expand access to sustainable and clean energy across South Asia. USAID and the Ministry of Power have together experienced, learned, and forged a partnership based on mutual understanding and a resolute commitment to energy security and access. This mutual journey of ours is thriving, and credit for that truly lies with the unceasing and dedicated support of the Indian leadership. I would therefore again like to thank Mr. KVS Baba and the POSOCO team for their unwavering guidance and support, as well as to the PGCIL team, including Manish Tiwari, for their engagement and the assistance they consistently offer to the GTG-RISE team. Additionally, many thanks to Deloitte, GTG-RISE's implementing partner, for their diligence with the pilot and in organizing this event. And again, to all today's participants, I'm so glad you've joined us. I'm hopeful that the lessons that we're learning here today will help propel us towards a robust grid here in India. I look forward to the presentation and to hearing from all of the other dignitaries. So with that, stay safe and stay healthy, and thank you very much. Back over to you, Manali.
Thank you so much, Julia. And Dr. Subir did join us in time, so we are lucky to have him just in time for his opening remarks. I'll quickly introduce Dr. Sen. Dr. Sen is currently working as the Chief Operating Officer, CTU, and Smart Grid Activities in the Power Grid Corporation of India Limited. Dr. Sen has more than 30 years of professional experience in the field of power system planning, system studies and analysis, open access, technology integration, and so on. He played a key role in the deployment of synchrophaser technology for real-time dynamic state measurement and deployment of smart grid in power grid. I'm really delighted to welcome you, Dr. Sen, for making your opening remarks. Over to you, Dr. Sen. Dr. Sen?
Yeah.
Okay, great.
Yeah, thank you, Madam Monali. So, and good afternoon to everyone. Sri Baba Saab, CMD POSOCO, Madam Julia Kennedy, Deputy Indo-Pacific Coordinator, USAID, India, representatives from Deloitte, India, distinguished stakeholders, and other participants. It's my privilege to participate in today's webinar, that is Knowledge Dissemination Workshop, an analysis of battery energy storage system applications in transmission system, being organized by our RISE initiative under Greening the Grid program. That is a joint venture or joint initiative of Ministry of Power, Government of India, as well as the USAID. So I am happy to inform that we met on 21st December last year on the occasion of Go Live event that demonstrated the testing of IT-based controls at power grid battery energy storage system installation at Puducherry, having total installed capacity of around 1 megawatt, and demonstrating an array of battery energy storage system applications on its stack benefits. And today, the results of those trial runs and test cases carried out since 21st December 2020 on various applications on a real-time basis, that will be shared with all by the USAID through the Deloitte people. So as we all know, so our power system is under transition. So drivers towards our emerging power system are basically providing round-the-clock quality supply to the end consumers, having energy security, reduction in the emission level, renewable integration, as well as resiliency into the grid, etc. So we are now focusing towards clean, flexible, and digital grade future power system with vision, electricity is the future. So now in this direction, with the increased penetration of renewable energy into the grid and more solar and wind energy resources, that will play a vital role. So it is targeted that the renewable energy share in the total installed capacity portfolio of our power system is to increase from present level of around 24% to about 36% by the year 2022 and 39% by the year 2025. So the renewables are having the peculiar characteristics like variability and intermittency. These are basically coupled with both the solar as well as the wind generation. So that poses a challenge to match the electricity demand and supply in every split second, which otherwise may have impact on the grid stability and the security. So thus, there is a need for a reliable, flexible, and adaptive grid. So energy storage system emerges as one of the critical elements to counter above aspects, ranging from like farming up of the RE output, then fast ramping, then energy time shift, reactive power support, even transmission capex deferral, as well as providing ancillary services. These are the various stack benefits we can derive from the use of energy storage system applications. So after go live event in December 2020, the developed battery energy storage system applications like renewable energy time shift, dynamic frequency regulations, peak shaving, renewable energy capacity farming, reactive power support, etc. were tested for a sustained period with real-time operation through designed hardware and software supported by the USAID. And the results of these test and trial runs carried out under actual grid conditions will be presented in the today's webinar too. The outcome of these tests will help us to assess the capacity of the battery energy storage system in providing various grid level services. So that shall go a long way to facilitate in policy advocacy on one hand, as well as framing the suitable regulations for deployment of the BESS in the grid in our near future. So we are confident that this joint effort of Power Grid and USAID with the support of Ministry of Power will prove a milestone in achieving the objective of for large scale deployment of battery energy storage system progressively in our grid in maintaining grid stability and resiliency. So with these words, I will stop my opening remarks here. So I will also listen to other distinguished speakers as well as the presentations on the on various application results, etc. So thank you all.
Thank you so much, Dr. Sen, for your kind words. We'll now move on to the next speaker, Mr. Baba, who needs no introduction, but quickly he's the CMD of POSOCO. With over 34 years of experience, he has deep knowledge of power system planning, power systems analysis, corporate planning, project management, system operation, market operation, and so on. And before joining POSOCO, he's also worked with NTPC and PGCIL. So I'm really delighted to welcome you, Dr. Baba. Mr. Baba, over to you, sir.
Yeah, thank you, Manali, for inviting me to this knowledge dissemination workshops. And first of all, let me say good afternoon to entire team led by Ms. Julia Kennedy, Indo-Pacific Region Director, and USAID and GTG-RISE team and Deloitte team who have been working relentlessly to make this happen. So I have to congratulate first of all of you for making this. And important point is that knowledge dissemination, as you know, POSOCO, we have always been talk about unless more and more information is made available, nobody can take the right decisions. So India, as Mr. Subir has covered, Dr. Subir Sen has covered most of the issues which I would like to say, but anyhow, not for the sake of repeating, I may have to few, and please bear with me. See, renewable integration is now one of the important aspect in our daily life, whether it is power system and all walks of life, in fact. So whenever we talk about renewables, we talk about flexibility is a co-synchronous with the renewables. So whenever we talk renewables, so automatically the flexibility comes. So we need many such interventions to introduce how the flexibility can be, flexibility in the generation, flexibility in the distribution, everything are handled. So we need to have more technical solutions, interventions. So how to directly, we cannot start introduction of all the technological interventions. So we need to load many pilots. These pilots, as Dr. Subir said, that it will give us more insights. So important point is that we need to study, we need to observe, understand, and these results are very essential to make proper formulations, proper models, to even including the financial models also. So that is very essential. As we all know, battery energy systems, storage systems are very essential, and it has a excellent features like, I mean, to start with the frequency corrections, because it is a fast response, it can provide the fast response. Similarly, it can be used for excellent resiliency. So because of its nature, we can use it for demand shaping, balancing with, once it is provided with the renewables like wind and solar. So and most important point of these inverters are that reactive power. To start with, we always feel that these batteries are the best components at the distribution level, because a lot of rooftops are coming, and all these rooftops. So as a distribution system operator, these battery backs will definitely and improve the power quality. So very important point is ultimately what all we do at the grid level or at the integration level, ultimately what we have to look for is the comfort of the consumer. So the power quality, so the voltage, frequency, everything has to be made available the right quantity and right quality to the consumer. So these battery, I mean, they have been tested. I mean, so we have to keep on introducing these things, and we have to learn more. So I'm also very eager to listen to the presentation of today's Deloitte, our GTG-RISE team, and what are all the benefits that are getting accrued, and what more we can derive out of this. So with this, I would close my opening remarks, and I wish the entire team all the best. And we need to have more such, and I hope the study report will be shared with us more, so that one presentation cannot understand the entire insights of the project. So we hope that this report would be shared with us, and for larger benefit of the entire system operator fraternity, or even for the investment people who want to invest also. So I'll be looking forward, and thanks to for inviting me once again to be part of this event. Wish you all the best.
Thank you so much, Mr. Bawa, as usual, for your words as well as for your support to the GTG-RISE team. We will be definitely sharing more information about this particular pilot, the findings, and Satish will be capturing some of the tools which has come out as a result of this particular pilot in his presentation. Before I request Satish to move on with the presentation, which is the highlight of today's afternoon rather. Can I request all the speakers to please switch on your cameras for a bit, and we can just take one photograph just to record it for our memories. And that would be great. Yeah, Dr. Sen, yes, thank you so much. Mr. Tiwari, can we also request you, Bhupi and Kakoli Pratik, please switch on your cameras. Yes, Manish ji, if you are able to, please do switch on your camera. Yes, although we don't see you. Okay, so Bhupi, please do let me know.
Some issue due to camera, yes.
Okay, no worries. We will transpose your picture there. Okay, thank you so much. Done, Bhupi?
Yeah.
Okay, great. Thank you so much for putting on your cameras and obliging us. I always end up making everybody do that. So thank you so much. So now let's move on to our presentation. It's by Satish. Satish is the director with Power and Utilities Consulting in Deloitte, India, and holds the portfolio of the Grid Integration Coordinator. He has been associated and he's been a key part of GTG-RISE project since the beginning. He has over 14 years of consulting experiences and focuses on large-scale RE integration, battery storage, EV deployment, and so on. Without further ado, I'll pass it on to Satish to share the results of the pilot. So over to you, Satish. We can't hear you, Satish. Satish, you'll have to unmute yourself.
Yes, sorry.
Yes, now we can hear you.
Yeah.
Okay.
So good afternoon, everyone. I'll just start without wasting too much time on the initial. So this is something on the Greening the Grid program, sponsored by USAID. And then I'll just quickly go ahead and share the technical discussion. So these are the pilots which has been constructed under the GTG-RISE initiative. And these pilots spans across battery storage system to thermal flexibility, automatic generation control, across solar and hydro units, and other kind of pilots, which are actually designed to manage the variability, which becomes very prominent once there is a large scale RE integration into the grid. So one of the pilot on the battery energy storage system in transmission is the point of discussion today. So we will just go on those things. So these are basic pilot scope outcomes. So this has already been discussed and highlighted by Baba sir and Subir sir also. And then these are the stages where we conceptualize the pilot. We also sought help from a grantee under the USAID program for enabling the hardware and software retrofits, followed by the testing and analysis. And at the stage 3, where we are now, we are working on consolidating the technical outputs from the pilot and the pilot journey so far, key hurdles, outcomes, what is the benefits, what is the way ahead on the battery storage transmission kind of deployment at transmission system level. So again, this is very quick snapshot. We started somewhere in 2017, followed by, we did a kind of grantee selection in 2018, followed by factory acceptance testing, go live demo in December 2020. And since last 3-4 months, we have been working on accumulating the overall technical data from all the applications, which has been demonstrated there. And now we are here where we are trying to present the key outcomes, the analysis, how we are, the battery is responding with respect to the control signals which it is receiving. Again, this is the basic architecture difference. So if you see, this is the original architecture where we have 2 different battery units, lithium ion and advanced lead acid batteries. They both are having independent SCADA systems. So each of the battery can be controlled individually. But here the intent was to demonstrate that in long run, when we are saying that a transmission system or grid level services would be required, and also there are space constraints. So we wanted to highlight that if we can control these 2 units through a unified controller, that would be a very kind of learning for any kind of deployment. Suppose if you are deploying say 100 megawatt in any any region or area or say state, and those can be controlled from a unified center instead of putting BMS and all those balance of plant at every of the units. So that we successfully demonstrated. We developed a new architecture. There is only one PCS controller, which is giving command to both the batteries accordingly. So ultimately the battery capacity, which is 0.5 megawatt and 0.5 megawatt individually, that is becoming 1 megawatt now. And similarly, there is always a kind of concept of integrating more battery energy storage systems in the same framework. So before I will discuss the key outputs, these are some nomenclature which needs to be understood upfront. So there are two battery units. There is a transformer which is connected and transforming the energy from the battery at 22 kV level. This is 22 kV feeder. There is a grid, and now we have new injection load also, and we have, so these are actually additions to the pilot, where we have installed a virtual kind of solar rooftop plant, and we have also fetched the metering data, and which has been provided to the CCU, the control block. Similarly, we have load points. This is a 22 kV feeder load, which we are measuring in real time. Apart from that, we are also, this is grid PCC power. This is actually import from the grid, and then the battery is there. So now the applications which we have demonstrated is like how to make this grid import PCC constant by the support of the battery, number one, where we are demonstrating two pilots, two kind of applications. One is peak shaving and the other one is load following. Similarly, how a new load, if installed there, can be varied with the support of the battery so that we keep this PCC power constant. Similarly, how to make this overall PV injection constant with the support of the battery so that the import on the grid is constant. So I'll just go ahead, but this grid PCC power is something which we need to understand upfront, right? So these are the enhancement in terms of controller unit design, then communication architecture, control logic development, which we did in-house with the support and guidance from Power Grid. And then I'll just start with the first of the applications, which is peak shaving application. So this peak shaving application is something where we are saying that my total import from the grid would remain within a pre-specified value. For example, if I say from 3 p.m. to 6:30 p.m., my total import from the grid should be between 1600 and 1700. This is peak valley value. This is peak value. But my intent is to keep the import from the grid between these two ranges. Accordingly, if I say that actual load, and what is the actual load observed at that time was 1432. So because this actual load is 1432, which is less than 1600, so the battery is charging accordingly so as to maintain the total import from the grid at 1600 level. These are the actual base response. This is charging. Similarly, from 1630 to say 1830, if I say my peak these band limits are between 1400 and 1500, the battery would respond accordingly so as to limit the overall import from the grid. These are the formulas, but these formulas we have designed, tested, and accordingly we are trying to showcase that the response is actual. This is instant response. There is no time delay inherent, and these values have been captured from the actual live system. Now, when we say this peak shaving, the practical application of it is something like we are trying to differ the capacity of a line. So, for example, if I understand that my total import from the grid is through two transmission line or feeders, and I want to say that my loading on this line should not be below 60% or 80%, something like that. If we want to implement, we can use a battery to do that very effectively if there is a larger capacity size. So here again, the same thing, which here we have just captured these snapshots in the next diagram. Here we are saying if 1500 and 1600 was my overall limit, how this load values would trigger the battery to charge or discharge in the real time. Right. So if this is 1600 and 1500, so and this is actual load value. Accordingly, if my load is beyond 1500, the battery is discharging, and again there is a toggle once this is again going beyond this 1500 value. Then again this is discharging mode. The other application is load following application. This is something similar to the earlier application. However, here the set point is a unique value. For example, we are saying that the total import from the grid should be fixed at 1500, or the total export to the grid is fixed at 1500. This is much more important in terms of when we are trying to give a schedule from the utility perspective. If I'm giving a fixed schedule for different hours, for example, from 1 hour, I'm saying I'll be providing you 1500 or drawing 1500 from you from the load point. And similarly, if I say that from these time periods, I'll be drawing only 1100 from the grid, or importing, exporting, both ways it works. And then the battery is having to maintain the set point by charging or discharging the battery. So for example, if actual load is above PCC point 1500 kilowatt, the battery is responding by 155, so as to make total sum equal to 1500, and similarly it is doing in the other hours as well. So this is again something to that, where we are saying that if actual load power, which is here, is something like that, how your battery is responding. So in case the load is more than the set value, the battery is discharging, and again there is a toggle whenever this value is changing, and the battery is again discharging. This is charging mode when the value is less than the set value. So load following is important when we want to do a kind of firm to follow a particular load, how a battery can be used to obtain a very fixed amount of output from the grid perspective, and also from a load demand perspective. So whenever there is a variation in your load, the battery is actually absorbing those kind of variations so as to provide a very clear output. Now, a third application is RE capacity farming. This is very kind of important kind of application, where we are saying that if I have a RE solar plant or wind plant, I can provide a very fixed kind of output as per my preset values. For every hour, if I commit that I'll be from a 10 megawatt plant, if I'm committing that I'll be able to provide 8 megawatt for 1 hour, then 9 megawatt, and so on. And that functions can be performed using this application, where we are saying that whenever your actual PV output is differing from the scheduled value, the battery pitches in and it balances out the overall power by charging or discharging functionalities. Right. So RE capacity farming is an important application where any kind of RE plants can be configured to provide a fixed scheduled power as per the actual requirement of the grid, and also the schedules which they need to honor. And also there is a DSM penalty kind of mechanism from which savings can be harnessed. Now I'll go to RE time shifting application. So this application is very simple one, where we are saying that the battery is charging as per the given time instruction. So if I say that from 10 to 12 p.m. the battery should charge, and from 12 to 14 it should discharge. So those kind of things are simulated here. However, in these formulas, if I put more variables here and say that okay, my charging would be initiated would start only when there is a surplus capacity, those kind of parameters you can put in here through a user interface. Similarly, discharging, if I want to discharge the battery for next 5 hours or 3 hours, I can put a lower rate of discharge, and all those limits can be setting. Now I'll go to voltage reactive application. So here again the concept is similar, that whenever there is a reactive power requirement, so battery is sensing the grid voltage or PCC point voltage, and then accordingly it is generating reactive power so as to meet for over voltage or under voltage conditions. These are the initial band. So if my overall voltage remains between say 21.7 to 22, the battery does nothing, the output is 0 actually. But whenever this goes beyond this threshold value, and then I have a fixed rate, this is a slope of the curve by which it has to generate reactive power. So here, if you say, this is actual voltage observed, whenever this is going below, the battery is discharging. Similarly, these instances, this is becoming idle. So this is second instance. But whenever the voltage, there is a over voltage kind of condition. So battery is charging and generating reactive power so as to compensate for the over voltage. Similar kind of detailed graph we have tried to capture here, that whenever the battery values are below the limit, so 21.75 battery is discharging. If it is between the range, the battery is doing nothing, and then again it is doing discharging function. Now this is interesting application, dynamic frequency application, where the intent is to modulate the output from the batteries so as to respond to the real-time frequency variations. And these are basically the control logics which has been fed into the controller. However, if you say that my initial frequency bands were 49.95 and then 50.05, and this is the actual frequency in the red kind of graph. And whenever this is within the band, the battery should ideally respond, and the output should be 0. But this response we are getting because there is a SOC kind of phenomena, that state of charge of the battery should be honored. And whenever the battery is doing whenever a battery is supposed to be in idle mode, it is also looking into the state of charge numbers. If my state of charge numbers are below or high, the battery would try to compensate and make the state of charge numbers between the pre-specified values. So here the output should have been idle, but there is a few values. I'll discuss in the next slide then. And again, if there is a variation like this one, so if it is between the range, it is ideal, because at this point, after some time, the SOC must have been brought back into the bands, and then it is becoming idle. Then this is discharging mode. This is because my frequency has gone below the lower band limit. And again, if this is between the range, this is fine. This is again charging mode. So battery is performing in real time. There is no time lag as such. It is responding to the observed frequency from the grid. And then we can set all these limits which are there, slope, parameters, how much charging, discharging you want. So all those limits can be set into the control algorithm. Right. So this is something where we wanted to just showcase how SOC is working. So SOC in this case, we have said that if SOC is more than 70, so then in that mode, the battery has to maintain the SOC by discharging function. So whenever, if you see here, even though the frequency was within the range, however, the SOC is 71. That's why it is discharging as per the formula. And if it had been brought back to 70%, the battery performs a kind of idle functions. It is not doing and not maintaining the SOC. So these are the 6 applications which we tried to capture through the actual system parameters and through the recording of the control system logs. However, we have also integrated, tried to capture some integrated applications. So the intent earlier was to showcase that the battery doesn't only respond for a particular one application, but it can be configured, because this is everything is electronics, the control logics, algorithms there. So how fine tune you do this logics controls, you can get the desired output from the battery system itself. So this is something where we are saying we have clubbed first 2 applications, peak shaving and load following. So here there would be 3 set points. So in peak shaving, we had 2 set points, the upper and lower band, and in the load following, we had a fixed 1 set point. Here, by one battery with loop, if my fixed set point for the load following is between the band of the peak shaving, the battery would try to maintain your fixed point and your load following application. But whenever that deviation is beyond the band, it will go back and toggle to the peak shaving application. So the same battery configured, deployed would function in both modes so as to maximize the overall benefit from the same battery unit. So these slides and other things will be sharing, so I'm not going into these details. So one detailed report will also be circulated somewhere in a couple of weeks time, or so that is already on the chart, sir. Right. So the other application was RE capacity firming and RE time shifting. So here what can be done is that if you provide that, okay, for during the daytime I will use RE time shifting function for say 4 number of hours. For remaining hours you can configure your battery to support the RE capacity firming functions. And here again, if you put few constant and variables, you can get the desired output as per the battery capacity, as per the actual grid requirement and others. So the third piece, we wanted to integrate frequency application along with voltage support applications. So the same battery can be configured to provide different P and Q outputs. For example, if I say that from the same battery unit, I'm going to use say 30% for reactive power support, 70% for the active power support. So the KV VA rating of the battery, that can be converted to P and Q, and accordingly we can get both the responses at the same time. So the battery is doing the frequency regulation function, but it is also monitoring the voltage regulation. Similarly, the other kind of application can be prioritizing the application. So for example, if I define that frequency regulation is of utmost priority to me, followed by voltage support, followed by load following, followed by this. So those priorities can also be assigned so that battery is toggling between these applications so as to maximize the overall output from the same battery unit. Right. So these are the key highlights, and then so key learnings from the pilot was that we had customized and designed the algorithms in-house based on the Indian grid conditions. Further, the same can be used by any utility who is trying to install or deploy a new battery energy storage systems, and same control logics would work very clearly, very fine. And also for anyone who is trying to upgrade their existing facilities so that they can see those kind of outputs at a larger scale. Apart from that, we also developed a new architecture that I explained, that the same architecture is capable of handling more than one number of battery units spread across geographies. And also one of the very important finding was the site acceptance testing guidelines that has never been attempted, and that is something which has been developed, and that will be very handy tool for anyone who wishes to deploy any battery energy storage systems at their premises. Right. So over to Monali now. Thanks, everyone.
Thank you so much, Satish. I understand that there are some questions, and for coordinating or moderating the Q&A, and also to deliver the vote of thanks, I'd like to now invite Shubhranshu. Shubhranshu is the leader of the Power and Utilities Consulting in Deloitte, India. He has over 24 years of experience in power consulting, spanning sector restructuring, business transformation, public-private partnership, power markets, and so on. Shubhranshu was the chief of party for GTG-RISE for the initial 2 years and is currently advising the program as the senior advisor. So I'll pass it on to you, Pattu, for the Q&A as well as for the vote of thanks. Over to you.
Thank you very much, Monali, and thank you, Satish, for that insightful presentation as well. We will go on to Q&A, and then possibly, I'll obviously come in and thank Mr. Baba in particular for staying on. I'm sure you'd also like to listen into the Q&A, so I'm just holding off, sir, for the moment, and also to Dr. Sen and Mr. Tiwari. Satish. Okay, so let's take in some questions, and we'll then move on to the vote of thanks section, I guess. Are there any questions, Ripu?
So there are few on the battery storage sizes. So battery storage size is 500 kilowatt each for lithium-ion and advanced lead-acid batteries, and that is total 1 megawatt capacity. on which these applications has been tested. So even though these are total size is not up to that kind of big size, but then also the actual testing has been done, and it has been foreseen that battery is responding as per desired control logics, and there is no delay, no kind of glitches as such.
Okay, battery maximum backup time, Satish, for both systems. Could
yeah, so this is actually 250 kilowatts. So maybe I'll ask Manish sir to take up this question. He will be having that.
Actual size is 500 kilowatt for 30 minutes. But if you are drawing less power, suppose 100 kilowatt, so definitely you can use that system for 2.5 hours.
Right. What's the maximum reactive power that battery can absorb? Any idea, Satish, on that?
Yes. So
And inject.
right. So for 500 kilowatt battery unit, so manufacturer has given a value that 400 kilowatt of equivalent to that reactive power can be absorbed or discharged. We have tested, and those are the limits actually. So that is there.
Right.
So Rajiv sir is also asking that have we checked that both the batteries can function in different ways? One is charging and another is discharging. Yes, that is possible. We tested that, but those results we have not showcased in this presentation. But that is true, that can be configured.
Any comparative analysis of the two technologies, lithium ion and lead acid? We have the performance. We haven't come out with the outputs yet, but yes, the differential performance characteristics have been captured.
Yes. So when we talk of the comparative performance, so one is energy heavy battery, one is power battery. Lithium ion provides more. So lithium ion responds to the frequency regulation kind of application. We have seen the stability there. There is a very minimum sluggish kind of behavior as compared to lead acid batteries. So there is a very nominal kind of difference, not a major one which we observed per se. And this
I want to add that we have been using these systems from 2017 for frequency regulation and energy time shift applications, and during this period we have found that their efficiency is different and their derating is also different. Those have been already presented in various forums earlier. The efficiency of advanced lead acid is less compared to lithium ion, and it is around between 75 to 80%. Whereas in lithium ion, it is near to 85%.
Right. There is a question on ramp rate limits for battery. Are there ramp rate limits for battery that we have from the manufacturer, Satish?
So manufacturer has given, so for the applications per se, so the initial applications which were designed were a frequency regulation. So there are no ramp rate limits as such. You can charge or discharge batteries to the maximum potential, provided you have SOC and other kind of technical parameters. Your BMS is fine and all those things. However, for the applications, we don't want the battery to charge and discharge for each cycle to the full extent. So those ramp rate limits we can impose through the control logics. However, there is no ramp rate limitations as per the manufacturer. Only safety purpose, BMS control systems, so the voltage spikes and all those things, those are there. However, those limitations are not there.
Right. I think there is one more question on future plans towards deploying BESS at higher voltages after this pilot. Yeah, so this was, let me take that on. I think in terms of applications, of course, this is what kind of tested the various possibilities, feasibilities. Now, clearly, we need regulations and a policy framework to be able to deploy at scale, right? So there is the move by CERC, as we all know, to bring out ancillary regulations, revamped ancillary regulations, which will have frequency response in the secondary domain as well as tertiary response. And hopefully that will open the doors for battery also to participate in frequency regulation. So that's one of the things that gets enabled. The other, of course, is in terms of renewable energy itself, adopting battery to integrate and participate in various forms in the electricity market, right? It could be for scheduling and avoiding DSM penalty, as Satish was outlining, but also to participate in energy markets of the future, whether it is through a CFD mechanism or in other forms. And there are clearly a lot of assessments being carried out as we speak by renewable energy developers with regards to how to integrate storage at source. And Satish spoke about one of the use cases there in terms of firming, the output of renewable energy plants through integrating storage, which we tested in this pilot. There are other applications clearly in terms of distribution segment, how to avoid peak, how to shave off peak, as well as other forms of application. The distribution segment, clearly that's something that distribution companies have also been assessing, and we have in the past walked you through a pilot assessment that BRPL carried out in Delhi under GTG-RISE as well. So these are all different applications, but obviously it's some distance off from policy and regulations to firm up to be able to really drive deployments at scale. But as we speak, the cases, in terms of working out the feasibility stand proven to a great extent, not just in this pilot, but across pilots, I guess. And there's a question on the investment cost of this particular pilot. Of course, this I'll let Mr. Manish Tiwari answer that. But just to bear in mind that this was deployed in 2017, and as planned out in 2017, I should say. And so this is, and the scale, of course, is fairly small. So this may not be the best benchmark, but I'll let Mr. Tiwari answer that question. And then we'll move on to the vote of thanks, I guess.
RISE, actually, it was on the tender was done in 2015 basically. So on those basis, it was on higher side. Now battery prices came down by half of that price almost.
Right.
So at that time, our lithium iron phosphate system was around 4.7 crore. And that advanced lead acid was 3.07 crore. But now prices are for 1 megawatt hour around 2 crores of rupees is there for lithium ion.
Right. So thank you, Mr. Tiwari. With that, I think we are on the top of the hour, so we'll bring this to a close. Let me start by thanking Mr. Baba in particular. He's been a constant support for the GTG-RISE program all through. And in terms of conception of these pilots, he's played a crucial role. POSOCO has been our primary counterpart. So the selection of the pilots and the entire thinking through. So thank you, sir, for guiding us all the way through. We're coming to the end of this GTG-RISE program in a couple of months. But it's been a great experience working all through with you in terms of giving us guidance all along. So thank you again, sir, and thanks for staying back and seeing the outputs of the pilot in particular. Dr. Sen, Chief Operating Officer of the CTU, has again been the pillar for this particular pilot, along with Mr. Tiwari. He was the first to really very quickly agree that this is something that is worth doing. This was a facility which was already in existence. We went in and enhanced some of the operational capability through the grant funding by USAID. And of course, with the work of the grantees, which happen to be KEC in this case. So thank you again, Dr. Sen and Mr. Tiwari, for not just, as I said in the past, being a great counterpart, but also challenging us all through, because that is exactly what brought the best in us and the grantees and all the implementing partners to the table. So thanks for the involved intense discussions and guidance all through. Ms. Kennedy, thank you very much for again being a constant guiding light. And this pilot was made possible to a great extent, at least the enhancements through the support under the GTG-RISE program, along with the grant funding also. So thank you again, ma'am, for for the entire support that we received from USAID all through. And finally, to Monali, who's a constant, as I said, guide, mentor all through, and for driving, not just this pilot, but all the pilots through to fruition. So thank you all. I hope you enjoyed this. We will, of course, bring a formal report out, and that will be shared that will be released publicly on our website as well, the GTG-RISE website. So thank you very much for attending, and I hope we stay engaged for future programs.
Okay, thank you, Subramshu, and all the team.
Thank you, sir. And please do join us for the next edition, which is so hopefully, we have some exciting results to share from the study as well. Oh.
Thank you all.
Then. Thank you. Bye. Thank you, Subir.
Thank you.
Thank you, Subirji. Thank you, Baba sir.
Thank you.
Thank you.
Thank you.
And thank you, Shubhranshu. Thanks, Panishji. Thank you. Bye.
Thank you. I'll just end it now.
Yeah.
Thank you, Subir.
Okay.
Thank you.
Thank you, sir. Thank you. Bye.